when we think about simulation, it's very powerful and very sophisticated. We have to think about what it can be used for, as well as constantly approach modeling and simulation and the power of these computational tools with just a great deal of humility. Certainly one of the areas that I think is very ripe for this is just the whole realm of scientific discovery. It's not just, oh, like now that we have AI, we can do this kind of thing. It turns out people have been talking about this thing for decades. So back in the mid-1980s, there was an information scientist by the name of Don Swanson. He said, imagine somewhere in the vast scientific literature, there's a paper that says A implies B. And then somewhere else in the vast scientific literature, there's another paper that says B implies C. So if you had actually read both of them, you would know that maybe it's true that A implies C. You can combine them together. What he called this undiscovered public knowledge, this idea that there's knowledge out there and it's public, but it's undiscovered because no one has actually connected these things together. He used the kind of cutting edge technology of the day, which was, I think, keyword searches in a medical database. And he actually found, I think, like a couple different examples. Since then, we've been developing more and more sophisticated ways of stitching all this knowledge together, which is all, I mean, ultimately really just part of this tradition of tools for thought.
Today, I'm joined by Sam Arbsman. You're a scientist, author, and a coder, and you're the author of this new book called The Magic of Code. And it's really something that we're going to be diving into this episode. But for now, could you maybe introduce yourself, tell us what you're working, and then we'll dive into all the coding stuff after that.
Sure. Hey, so great to be chatting with you. I'm Sam. My current role is scientist in residence at Lux Capital. So Lux is a venture capital firm. We have over $5 billion under management, and we are kind of in the realm of emerging tech, frontier tech, deep tech. People use lots of different terms. I think probably the most accurate way to describe it is we're playing at that boundary between science fiction and science fact. We're just very interested in kind of trying to take really crazy out there ideas, whether it's in AI, robotics, biology, outer space, and try to bring them into the real world. And so my role is not on the investment team. My job is to really survey the landscape of science and technology and find areas or individuals or communities or topics that could be relevant to Lux and kind of bring them into the orbit of Lux. Sometimes connecting those to the companies that we've already invested in, but more often than not, being pretty far upstream from investment and kind of like laying the groundwork for when those ideas and topics might be relevant for investment. And the truth is sometimes those areas are never ripe for investment. So I actually spend a lot of my time thinking about non-traditional research organizations, but it happens to be that some of the most interesting things and most interesting people are working in those spaces. And so I kind of just bring them into the orbit of Lux as well. And so the way that kind of cashes out is I spend a lot of my time engaging with the public and writing and speaking and talking to interesting people. And so, yeah, and so part of my writing is I wrote this new book, The Magic of Code, but this is actually my third book. I have two previous books, The Half-Life of Facts, which is about how what we know changes over time, and Overcomplicated, which is about the increasing incomprehensibility of our technological systems, and then how to think about that. And then, yeah, I do a whole bunch of other writing and on many different topics. But yeah, I'm excited to chat with you.
That's such a dream job, it seems, at least from the outside.
It is a lot of fun. I feel very fortunate.
Yeah, well, I'm sure you worked for it. Well, so I'd like to start with your current book that you have out now, because, yeah, like I mentioned, it's called The Magic of Code. And could you just, before we dive in too deep on this, I'm not a coder myself, so I'd love to just get an explanation from you. What do you talk about when you talk about coding? Like, how would you explain what that is, even if we start very basic?
Yeah. To be honest, what coding consists of it is a moving target. It's changed throughout the history of computing. It used to be, very early on, it was like flipping switches or kind of plugging things in. Then it moved towards like writing things in binary or then machine code. And then now we have kind of more human readable code. It's going to change going forward with AI. But ultimately, it is, I would say the most common way to think about it, it is text that is kind of this very logical, rigorous way of just of telling a computer what to do. And the more highfalutin way to think about it is it's taking ideas and maybe algorithms and rules or concepts in your mind and somehow instantiating them into instructions for a machine. And so the most common ways are kind of using the sort of the popular languages that we have, like Python or C++ or Java, or there's many different, or JavaScript. And these are all specific languages that they have features of natural human language, but also features of, I would say, things that kind of border on mathematics. And they're kind of this weird in-between thing where there's a certain type of syntax, a certain set of rules and how you write these things. And then you write like, you write code like as it's text, and then you give it to the machine to run. And so it's this weird thing where it is text, but it has this impact on a machine. Like you are actually controlling it, which kind of is one of the reasons I write about sort of the magic of code, where it ultimately, I mean, it is the embodiment of things that we've actually been desiring for millennia, of like using text and words to control the world around us. Like that, to a certain degree, that's wizardry and sorcery. And we now can do that kind of thing using code. So I would say that's a high level description. I'm happy to dive in more into lots of different details there.
Well, why don't we also dive into why you wrote the book? What brought you to write this book? Because I'm assuming you thought a lot about coding, obviously. And so, yeah, I think that would also like help us structure maybe all the different facets of it, because you go into different angles of it throughout the book, basically.
Yeah, so I mean, I would say there were a number of different, I guess, reasons that kind of caused me to think about this. I would say, I mean, certainly one of the things that I think about right now is when I look at the current conversation in our society around how we think about technology and computing, it feels somewhat broken. I mean, so there's, for most people who are outside of the world of code and software, many people are adversarial towards it. They're kind of worried about it. Sometimes there's a certain amount of ignorance. And the truth is, a lot of these concerns are valid. But when I think about my own my own childhood experiences with computing, while I mean, there were certainly elements of concern and control and things like that, it wasn't really like that. Like when certainly when I learned about like early computing and computer science, it wasn't even just, I didn't even view it as just a branch of engineering. I viewed it almost as this like humanistic liberal art that in the process of thinking about computers, it would connect to language and philosophy and biology and art and how we think in all these different areas. And so my attempt with the book was to kind of rekindle some of that kind of wonder that I remember and try to give people, both who are experts as well as people who are coming from the outside, a sense of just how grand and all-encompassing thinking about computing can be, and try to, yeah, rekindle and bring back a little of that delight. So like when I think about like my own childhood experiences with computing, it wasn't just worries, it was also, I don't know, fractals and weird algorithmic art and Sim City and like early computers like the Commodore VIC-20. It was like a whole bunch of weirder things. And the truth is a lot of those kinds of things and those kind of ideas are still around now. And sometimes though we've just forgotten them. And so the book steps through various different aspects of code and the way in which it kind of impinges upon various aspects of our lives, but from the perspective of thinking of it as almost this humanistic liberal art that touches upon all these different domains.
I think one of the things that I picked up on that seemed really interesting to me was that you said that it's a tool for thought, also coding. Can you maybe unpack a little bit more what that means and like how you think that it changes the way we think or reason about things, basically?
So the idea of a tool for thought is really just, it's, I mean, a tool, it's like some sort of technology that changes or enhances our ability to think about various different topics about the world or whatever we're kind of trying to understand. And the idea of a tool for thought is, it's, I mean, people talk about it more right now. They often think of it in terms of computing, but ultimately it is a very old technology. If you think about it very broadly, I mean, the alphabet, literacy, paper, these are all tools for thought. Like the fact that you often are told by your teachers to show your work when you're doing a math problem. Not only is that maybe a way of giving them, of you being able to get partial credit if you get something wrong when you're in school, but it also actually enhances your ability to think through things because you don't have to keep all this information in your head. You're able to include it on paper through manipulating bits of information and writing things down. And so so tools for thought are very broad. And it turns out when it comes to computing, there's kind of two different interconnected ways of thinking about tools for thought. There's both the idea that code itself can allow us to think through problems. So for example, having a specific programming language or actually trying to instantiate a problem in code, that in itself will actually give you a better understanding of a thing. So if you say, oh, I have this problem, how do I, and you have sort of like a hand wavy understanding of it or a hand wavy approach to solving it, that kind of hand wavy thing will not work for a computer. Computers are very literal, they require a lot of detail. And so in the act of thinking through how to solve a problem, and actually explain it or kind of allow the solution to be done by a computer, you will actually have thought about the problem better. So there's that kind of very specific thing. And then there's also other details in terms of how different programming languages might affect how we think about the world, which I can discuss as well. But then there's also the idea of using computers themselves as tools for thought. And it turns out this actually has a fairly long history within computing, where very early on, people were thinking about computers not just as vehicles for like massive scale simulations or other kinds of things, but also as tools for education. And especially once people started thinking about computers as a little bit more personal, that certainly was a very important aspect of that. And so people have been talking about this idea of, can we use computers and software as a way of elevating the kinds of thoughts we can think about, whether or not it's connecting different ideas, let's say in scientific domains together, or helping with brainstorming or whatever it is. This is this idea of the kind of tool for thought. And and you can see, there's a long history of this kind of thing. So, for example, it can be as simple as like a spreadsheet. The idea of being able to model some simple scenario in a spreadsheet that can actually aid your thinking. But again, going back to what I was saying, like this, and then there's also people who are kind of very involved in the early days of Xerox PARC and some of the early personal computer ideas. They were also thinking about these kind of tools for thought. And of course, now with the advent of certain like generative AI and LLMs, we really have the ability to kind of do this sort of in overdrive. And the way I kind of think about this is ultimately these large language models, they are taking huge amounts of text and information and embedding them in this kind of virtual latent space, this like high dimensional space with lots of concepts and ideas. And once you have that, you can then navigate that and actually connect different ideas together. And so certainly one of the areas that I think is very ripe for this is just the whole realm of scientific discovery. And again, this is actually not a new thing that people have, it's not just, oh, like now that we have AI, we can do this kind of thing. It turns out people have been talking about this thing for decades. So back in the mid 1980s, there was an information scientist by the name of Don Swanson. And he had this idea of, it was a thought experiment. And he said, imagine somewhere in the vast scientific literature, there's a paper that says A implies B. And then somewhere else in the vast scientific literature, maybe in the same subfield, maybe in something else, there's another paper that says B implies C. So if you had actually read both of them, you would know that maybe it's true that A implies C. You can combine them together. But of course, no one has actually read either of those papers because the literature is just so big. And so what he called this undiscovered public knowledge, this idea that there's knowledge out there and it's public, but it's undiscovered because no one has actually connected these things together. And he was not actually content leaving this as a thought experiment. So he used the kind of cutting edge technology of the day, which was, I think, keyword searches in a medical database. And he actually found, I think, like a couple different examples of doing this kind of thing. And so I think one of them was he found a potential relationship between consuming fish oil and helping treat some sort of circulatory condition. And then actually published it in a medical journal, even though he was not a physician, as far as I'm aware. And of course, since then, like this is a very rudimentary thing. Since then, we've been developing more and more sophisticated ways of stitching all this knowledge together. And I think now with certain techniques, there's a lot of people trying to use these systems to say, okay, how can we actually navigate this to come up with better hypotheses and ideas and even scientific discovery, which is all, ultimately really just part of this tradition of tools for thought.
Just on that tangent or like that, Fred, do you have any examples of which orgs or people are doing the most interesting stuff in AI for science right now?
There's a number of different, there's companies and nonprofits that are kind of all playing in this in like different areas. And so some are helping you look through the scientific literature. I think there's at least one company that I've seen that is maybe helping with like hypothesis generation and even like experimentation testing. I'm not sure how many of these are public or things like that. So I'm not going to give any details or names, but there definitely is, I think, a lot of really interesting things happening here. And because I think this idea that, like, on the one hand, science has become like so vast and in some ways sometimes a little bit more difficult. People have talked about whether or not the pace of discovery is slowing down and things like that. And or maybe it's still continuing a pace, but we just need to put in more and more scientists and more funding and things like that. And one way of potentially allowing for a speed up is actually using this like human machine partnership and actually using AI to kind of help with generating hypotheses and ideas. And so, yeah, so there's a lot that is happening here. It's super, super exciting. Still all very early, but yeah, I think that's going to be one really interesting avenue in terms of how people think about science going forward.
And do you think in terms of if we think about these tools for thought in a more like intentional way than we have maybe historically, the AI for science is like one angle, obviously. Are there any other angles, or if we consciously just try to make the most of this like tools for thoughts in terms of coding, what would you want to see basically?
Yeah, I mean, so and another one is just in terms of even like how we think about education and like retaining information. So oftentimes you might read a book and enjoy it and learn a lot while you're reading it, and then I don't know, a couple of weeks later, someone asks you about it, and you really all you can remember is like the top line kind of takeaway. Maybe it's encapsulated in the subtitle, and you're like, I don't really remember all the details. And sometimes that's not necessarily bad, but if you really want to understand some of the information in great detail, you might need new ways of actually absorbing that information. And so there's a number of research. So for example, Andy Matuszak has been doing a lot of work in terms of like how to think about like reading and books as sort of like a new type of medium, oftentimes in conjunction with these kind of like more digital versions of these things where you're being tested for information and then you kind of are using sort of like space repetition to eventually be reminded of these things and remember them. And that is a really different way of reading than I think many people read when they just read books. But it actually has the potential for really being able to absorb a lot more information and potentially use that for new ways of thinking. There's also, and going back to coding itself, another thing that I think a lot about is ultimately writing software is the encapsulation of thoughts and ideas that the coder has into code, like into software itself. For a long time, that has been the domain of experts. Like you have to be an expert in writing software, you have to be trained in these kinds of things. And so oftentimes, if you are a subject matter expert, but you're maybe not necessarily familiar with coding as much, you have to either outsource that and work with other people who can actually take your ideas and put them into code, and you might need like a lot of funding to do that kind of thing. Or you just will have to say, oh, I have this cool idea, but I can't really do anything with it. And alongside, obviously, teaching software and like teaching software development, there has been another tradition, which is this idea of democratizing the act of software creation and the ability to allow anyone to write software themselves. And I actually view that to a certain degree as another kind of tool for thought, because if any single person can build the software they want rather than saying, oh, I have to think about potential market of millions of people and the ability to scale in order to get funding. If I just want to build something for myself, and historically you've not been able to really do that. But this democratizing software movement, which has been around also for a long time, really does allow everyone to use software and programming as a tool for thought, a way to do their things. And so, I mean, and people have talked about this idea as end user programming, the idea that rather than the programmer is developing the software, the end user, the one who's actually using it, can modify the software themselves for their own needs. So rather than it being like, oh, here is a piece of software that's one size fits all, no, I can manipulate it and modify it and make it whatever I want it to be. And certainly with generative AI solutions and like the advent of vibe coding and similar kinds of things, like it really is changing and lowering the barrier to allow anyone who has ideas to build things. And so I'm reminded of, there's a wonderful essay by the novelist Robin Sloan where I think the title is something to the effect of "An app can be a home cooked meal." And the idea is like, rather than, certainly you can cook for like hundreds of people in a restaurant, or I don't know, thousands of people at some sort of large like convention center. But by and large, when we cook, we can just cook for ourselves and for our loved ones. And we should be able to do the same kind of thing when it comes to our software. And this massive democratization, which I mean, in some ways we're there, I think there's still a lot left to do. That really opens up our minds to now being able to just look at the world and say, oh, if I have some interesting, weird idea for a game or some enhancement to the software that I use on a daily basis, that now actually is possible.
I love the metaphor of a home cooked meal because then you can do it exactly how you like it, if you want coriander on or not. And I actually wanted to ask you also about vibe coding, so I'm glad you brought it up because yeah, it's a term I've been hearing people use a lot more. And basically, as I understand it, it's like when people use LLMs to write code, so you don't have to be as skilled basically to code. Do you have any takes on that shift in general? Because it obviously seems like it would just change our relationship to coding. And if that becomes dominant, would that change things at a more broad scale? Or yeah, what do you think of this shift, basically?
Yeah, so I think vibe coding, as it was kind of originally discussed, was really almost using a conversation with an LLM to generate software and then never actually looking at the code at all, just kind of taking things as given. And one very interesting take by Steve Krause, he's the head of a company called Valtown and also very involved in the future of programming and coding community, is I think he described it as vibe code. Vibe code is basically legacy code. And so legacy code is, it might be code and software that was written a long time ago that maybe everyone, so it might be like you're working for some large company and there's software and code that was written by people who are long retired or maybe even dead. And so no one really kind of knows how it works. It's really essential for everything to run, but there's no real understanding of what's going on under the hood. And I think that kind of analogy is powerful where like if we don't have the ability to interrogate the code itself, and we kind of just take it as given, then we are abdicating a certain amount of responsibility for understanding it. Now, if it's for a home cooked meal, maybe that's fine. But if you're using vibe coding for things that are going to be used by a very large number of people, that doesn't feel as safe or as responsible. And so for me, on the one hand, and so for me, I wouldn't use vibe coding that way. I certainly, but I think the like AI enhanced coding is probably that's the right level because that encompasses also a much broader set of activities. And that is actually really powerful because it means I don't have to remember certain syntax details or specific libraries or whatever. I can kind of just go a lot smoother and faster in programming. That being said, I think the ability to understand a certain amount of code that's being generated really does allow you to manipulate the resulting code that much more in a much more sophisticated sort of way. And so I would say, so I'm kind of multiple different minds. On the one hand, I think understanding kind of traditional code will still be vital in many different ways because we want to make sure that AI generated code is not legacy code. Like it actually has a certain amount of understandability. And so, and being able to dive into that and understand it. The other thing is also just when you are given code that's AI generated, it's sometimes a lot easier to manipulate it directly. And that requires a certain amount of understanding. That being said, I do think this ability to generate code will lower the barrier to learning how code works and learning how to program, as well as just allowing people to try so many more different things. And so there's the computer scientist Seymour Papert. He was involved in the creation of the programming language Logo. There's a kind of famous phrase attributed to him, which is this idea of like low floors and high ceilings, where it's like you kind of want things to be very easy. You want a low floor, but you want there to be a great amount of expressiveness and open-endedness. And that's the dream of low code or no code or vibe coding or democratization of coding or whatever these things are, because you want it to be easy for non-programmers. But as you gain a little bit more facility with it, you should be able to say, no, the sky's actually the limit. I can kind of do anything I want. And so I certainly think that AI generated code or AI enhanced code really will open up a lot of doors and allow people to build things in ways that they never thought they would be able to do because they just thought, oh, I don't think of myself as a coder. I can't do that. And now you can actually do those kinds of things. On the other hand, though, we kind of just have to still be very like responsible with it. I think also I think right now it's still very early days in this. Like and one of the things I think I've seen other people talk about this as well is it's great that we can generate code, but like right now when we use AI systems, by and large, we're using like a chatbot interface. And the chatbot interface is probably not the right interface for making sophisticated software, especially if we want it to be graphical and visual. Like maybe we need very different sorts of interfaces. And so I think we're still figuring out the best way to actually generate software using that kind of approach. But I am cautiously optimistic for really opening a lot of really interesting avenues. And which is also the kind of thing where it no longer then is the job of programmers to say, I know all the different features that people are going to need for the software. Each person can decide for themselves. And I think not only does democratization, like it's really almost like a democratization of creativity at that point. And I think that's really exciting as well.
Yeah, that always seems exciting, or like just making it accessible to people in that way. Yeah, it definitely makes me want to try it. So I haven't yet, but I should. I'm not sure how to phrase like this question, but I feel like you touched on it a little bit with vibe coding and stuff. Is that with a lot of coding, it seems like we don't really understand it. Is that, do you agree that's the case? And does that matter?
So it kind of depends at what level you're thinking about it. On the one hand, I mean, one of the most fundamental ideas of computer science is the idea of abstraction. This idea that like when you write a piece of software or a computer program, you're not starting from scratch. Like you're not working with just like the raw binary. You can use all the different libraries and features and higher level programming languages that have come before you. And so that allows you to, like, if you want to, I don't know, do some sort of sophisticated mathematical manipulation, you don't have to figure out the algorithm for all those different details yourself. You can just take a programming package and like off the shelf and then use that in your computer program. And the same kind of thing is like when you're, I don't know, trying to stitch together different systems, like you can kind of abstract away the details. And in that sense, yeah, I don't necessarily know all the details of how these packages and libraries and modules are doing their thing, but I kind of operate on the assumption that they've been tested and they're kind of well understood, and I can just kind of use the interface without having to dig under the hood. That being said, obviously there are certain times when abstracting away the details does not work, and like you have glitches and failures, and like that's sort of like the hallmark of not necessarily understanding a system, where you kind of there is this gap between the system as we thought it operates and how it actually does operate, and into that gap is all the failures and glitches. And certainly as we build more and more sophisticated computational technological systems, these kinds of things become more complicated or become more likely, because the systems that we're building have, I mean, a huge number of interacting parts. They might have accreted and built and become more complicated over time, very long periods of time. So we're contending with legacy systems and legacy code where people do not fully understand these things. And they're just kind of connecting to lots of different things, or they have to just simply contend with the increasing like messiness and edge cases of the world. It's like the real world is really weird and messy. And so therefore, computer systems are going to also have to engage with that kind of thing. And so as a result, we do end up with software that we just don't fully understand. Like in the sense of like it is too large and too complex for any single human to possibly hold it in their head at any one point. And it can be actually a fairly small computer program that is kind of beyond mortal understanding. And I think on the one hand, it can be worrying. There are ways of making sure, like maybe modularity and things like that, to make them more understandable. For me, it's just a matter of being aware that we are already living in this world that is increasingly incomprehensible. I think most people, they assume when they're looking at technological systems, oh, these things they're technologies, they're rational, they're made by people, therefore we should understand these things. And that's not really the case. And so when we are confronted with failures and bugs and glitches, we can learn more about the systems by seeing where they fail. But oftentimes people who assume that these systems should be much simpler, much more understandable, they're blindsided by these kinds of things. And so for me, I just want there to be a greater awareness of the vast complexity of these technologies that we're building. So I remember this is years ago when the Apple Watch first came out. I read some article, I think it was in the Wall Street Journal, about whether or not mechanical watches would still be a thing, like whether or not they would still be popular. And of course people are still buying them. But they interviewed this one guy and he's, of course I wouldn't want to use a mechanical watch. I think about the vast complexity of a mechanical watch as opposed to a smartwatch, which is just a chip. And I'm thinking like just a chip, like a chip is orders of magnitude more complicated, but we've been shielded from it. And so for me, I just want people to be aware of that complexity, because also when we think about understanding, like it's not an all or nothing proposition. It's not, oh, I either fully understand this system or I'm in total ignorance and then things are just going to go wrong. There's a really complicated spectrum, and we can slowly but surely move towards greater understanding. And I feel, and we're already like well positioned for doing that kind of thing. Like when we think about biology, it's certainly like human beings, like we don't fully understand human beings, but we have ways of trying to understand ourselves better and better, whether it's cognitive science or biology or neuroscience or psychology. Like, these are techniques to slowly but surely understand vast, complicated systems. And I think we kind of need to use those same sort of like mental approaches to thinking about even technologies of our own making. Like when these things are like so complex that they verge on being like organic in their level of complexity, maybe we have to take a page from biologists in terms of how we think about these kinds of things. And there are actually people who try to use these kinds of techniques or think about what this would mean when approaching like AI systems and things like that.
Yeah, I think you touched on a few things that I wanted to ask you about already, which is because I think my favorite part of the book was the last part where you talk about reality. And you do write a bit about biology and like how biology and software like increasingly overlap, I think. could you maybe explain that a little bit more? And also like, where do you see this going? Do you see like a future for like biocomputing or stuff like that?
Yeah, and so the way I kind of think about this is, there's at a surface level, like very simple things we can say about like the similarities between biology and computing. We can say, oh, in the same way that computers use zeros and ones, biology uses the four bases of A, T, C, and G for DNA, and then and like you kind of have like transcription and then like programs being run in biology and like within the cell, and it feels very similar. The truth is, though, what I discuss in the book is like there's kind of two ways of thinking about biology. There's kind of the information view, which is the one I kind of described, where it's like you have like streams of information that are being run and operated on and things like that. And then you have the mess, which is we are, I mean, like at the human level, we're kind of just like wet, squelching systems and plants are dirty. And then you have down at the cellular level, like massive amounts of randomness and stochasticity and everything just kind of like vibrating weirdly. And that feels very different than kind of the information view. And so biology, I kind of view it as like it has certain computational features, but it also is in some ways radically different. But in truth, one of the things that a number of scientists have talked about is this idea of like biology has computational features, and I think we are increasingly getting better at encapsulating biology in software through like simulation and modeling and things like that. But we're also realizing that biology is almost a like a superset, or at least another aspect of some larger thing, which is just information processing. So when people say, is a cell a computer? Yeah, it's a computer, but not in the way that like my laptop is a computer. Like it looks nothing like that. But it is computing, it is processing information, but in a vastly different way. It's more parallel, it's much more stochastic, it's very different. And so I definitely think that there's something to be said for the more we understand biology, what's happening at cellular level, what's happening at higher levels of hierarchy, it will actually give us a better sense of the true suite of possibilities of how we might actually be able to compute. And so we could, yeah, eventually, like in this, I think people have done things where they have used DNA as a means for like factoring large, like huge numbers, like into like their like prime factors. And then people have also like slime molds to help do like optimization problems and things like that. And so I actually think there's some very interesting things around using ideas from biology or blending biology and kind of more traditional computing to allow us to actually think much more broadly around this idea of information processing and computing more broadly. And yeah, so there's also other things just like in the way we write software. It's traditionally, oh, you write a little module and it connects to other modules or whatever, and it's kind of very functional. Biology doesn't do that. A single like enzyme or a string of DNA might have a whole bunch of different functions that are all kind of overlapping and weird and happening at different hierarchies. There are scientists who call this, I think, polycomputing. And it kind of just shows you there's just a totally different way of computing. And so I love thinking of biology as both deeply computational and we are kind of blending these things, but it also is a window into so many other ways of computing.
That's really interesting. I think that the another thing that this leads to in terms of also that you write in the book is this line between like artificial life and emergent behavior in software. Could you maybe just tell us a bit of what you think about that boundary between machine and life? And do you, for example, think that we'll actually reach a point where software entities could exhibit something like agency or intention or like consciousness?
Yeah, and so yes, the idea of artificial life is it's this domain of research that I think first became a thing maybe in the late 80s and kind of had its heyday maybe sometimes in the 1990s and went through a quieter period, but now is actually having a certain amount of resurgence, which is actually really exciting. But it's basically this idea of thinking about, I think that the phrase people talk about is life as it could be. So rather than saying, oh, like the one form of life that we can study is biological life on Earth. Obviously, there's many different types of life, but it's all kind of fundamentally the same, has all kind of the same parts. Let's actually kind of try to understand life as what are its like most fundamental features and see if we can encapsulate those kinds of things in silico, in computer programs, and then in the process learn about how life works, what is actually necessary for it, and maybe also figure out what is the true breadth and like this in this high dimensional space of what life could actually be. And so one one very basic feature of life is the fact that it evolves. It has evolved over time. And so there's an entire space of research around like evolutionary computation and genetic programming and genetic algorithms, kind of using the idea that ultimately evolution is really an algorithm for allowing change. It's almost like an optimization algorithm. And so using like encapsulating those ideas within software and then evolving computer programs or bits of information or whatever to actually understand how evolution works, why it sometimes plateaus, how to overcome that kind of plateauing. It's a huge field and there's so many things happening in there. That's kind of one example. But more broadly, going back to what you're saying, will we eventually encapsulate life itself in software? Like, will software eventually be considered living? I'm going to be kind of fairly agnostic on that one. I think in many ways, and I think in principle, that is certainly possible. I don't think there's any sort of like magic stuff kind of overlaying life. It certainly is a physical process. And I think the more we understand it, we realize there is this kind of computational features to what life is and how it works in terms of information processing and things like that. Are we there yet in terms of actually having encapsulated? I don't know. Probably not. I feel comfortable saying that's probably unlikely that we've already reached that kind of thing. But certainly between advances in AI and evolutionary computation and other kinds of things, I think, we're like, there's some really interesting potential avenues here for just kind of the realm of artificial life, of like how to think about life in silico and what that future holds. So I'm not sure we're quite there yet, but I am very excited for what the future holds, less about like actually embodying biology in life and much more about using software as a means for better understanding what life is. And so, yeah, whether or not we'll say, oh yeah, like in 5 years, like we're gonna have these like a vast computational sea of virtual bacteria or whatever it is that actually really will exhibit every aspect of life. If we build something like that, that'll certainly teach us about how life works. And so I'm really excited about that too.
You mentioned simulation also here. What do you think what can we gain from simulations, basically?
Yeah, and so simulation, I mean, that's also one of these things that we've been doing since the advent of modern digital computers. And so like you look back to some of the earliest computers in the late 1940s and early 1950s, and they're doing like, I think like large like nuclear simulations and things like that. So we've always been wanting to model and encapsulate the world, or at least a subset of the world, in computer programs, because it's kind of this interesting combination of using mathematical descriptions to explain the world, but also actually having those descriptions be dynamic. Like they're not just inert. Like I'm not just writing an equation and kind of sits there and you can kind of think about it. But they can actually now come alive. And that's one of the really fascinating features of computers. And one of the exciting things is like kind of through the confluence of massively more powerful hardware, better data, better algorithms, we are now just able to simulate more and more of the world with higher and higher fidelity. And so one of the examples I discuss in the book is around like weather prediction. And so in weather, I feel like a lot of people kind of maybe like unfairly malign weather prediction of, oh yeah, like the weatherman said it's going to rain this day. And of course it's like not, it's like totally wrong or whatever it is. But the truth is, because of those trends in advances and like in computing power and the like, our ability to simulate the future weather has actually improved quite steadily over the past like decade or two. And it's gotten really sophisticated. That being said, I mean, the world is really complex and like complex in ways that we just don't even understand yet fully. And so for me, when I think about simulation, it's not to say that, oh, we are automatically going to bump up against lots and lots of limits, although there are certain things around like chaos theory and stuff like that kind of point towards maybe theoretical limits. But for me, I think about simulation, and there's simulation for prediction, but simulation doesn't necessarily need to be just for prediction. There's so many other reasons. And I would say one of the most important reasons, aside from prediction, is for understanding. And when you build a very complex model of the world, maybe it has predictive power, but you often don't necessarily understand how that very sophisticated model works. And so for me, like when I think about like SimCity is a computer game, it's a lot of fun. Does it accord with the way cities work? No, it's like a vast simplification. And in some ways, it's probably just like outright wrong. But when you play SimCity, you are like certainly like as a kid when I was like encountering it, like that was probably the first time I encountered like a complex system that I could manipulate that would have unanticipated consequences, that when I did things, it would bite back in unexpected ways. And it really gave me a a certain amount of intuitive understanding of complex systems, as well as a certain amount of humility in how they operate and how much control or lack of control I actually have. And certainly, the more sophisticated we make a model, if it's not too complex and provides us with understanding, it can give us that kind of understanding. And that kind of understanding is very different than saying, oh, now I understand exactly how a city works. I now understand how certain fundamental features of complex systems, but not necessarily how a system works or how a city works. And so I think there's a number of different reasons why we might use simulations. And I think when we think about simulations, we always have to have a certain amount of humility. Like we're on the one hand, we want to make a simulation that's so sophisticated it is as complex as the real world and really takes the entire world and you can pour it inside a machine and it does exactly what you want. We are nowhere near there yet. And so I talk about Laplace and Lovecraft as kind of these two extremes. So like Laplace, he was a French scientist and he kind of had all the thought experiments around like sort of the clockwork universe and explaining everything. And if you knew every single like molecule and atom in the world, and you could then just kind of run an entire simulation. And I think to a certain degree we want that kind of thing. On the other hand, though, there's H.P. Lovecraft, the horror writer, who's like, oh yeah, we barely understand this like thin veneer of the world, and there's like all these like horrifying monsters that are out there and things. And it's kind of, and if we truly understood that, we would like humans would go mad. Madness aside, I think we have to at least have a certain amount of humility when it comes to understanding the world and even our ability to simulate it. And so there's actually this wonderful book called Fluke by Brian Klaus. And in it, he kind of talks about just the sheer amount of like randomness and unexpectedness that is even in systems that we think we fully understand. And so I think when we think about simulation, it's very powerful and very sophisticated. We have to think about what it can be used for, as well as constantly keep the tendencies of Laplace and Lovecraft in tension and just approach modeling and simulation and the power of these computational tools with just a great deal of humility.
Yeah, sounds wise. The world is very complex, but very useful, obviously, to be able to use simulations. I was thinking that maybe we'll leave the magic of code a bit, and unless you think there's anything like that we've missed that you think basically would be important for that could steer our future in terms of coding. But basically, I wanted to also just like touch on because you wrote two other books, like you mentioned, and I think if you've spent so much time writing a book, it's probably an idea that you thought a lot about. So I would just want to touch on like those two books as well.
Sure, no, that's fine. And I think actually, I mean, ultimately, I've noticed one of the themes in a lot of my writing has just been this approaching the world with a certain amount of humility. And like my first two books are very much about that. And I think even the third one around the magic of code is like computers are really powerful, but we have to think about their powers in kind of context with like our humanity and sort of be humble in the way we approach things and just be very deliberate in how we use these systems. So yeah, no, I think there's a lot of connection and yeah, happy to discuss that more.
Yeah. No, and I love the humility point as well. I think that's it's just extremely important because we don't really know what we're up against, I guess.
Yeah.
Uh, so your first book is called The Half-Life of Facts.
Mhm.
So could you maybe explain what you mean? Like, why are you talking about the half-life of facts? And we could even talk about it an approach to learning something like coding, that maybe things are always changing, is what I take from the book.
Yeah. So the idea behind the half-life of facts is on the one hand, like we know that what we know in terms of our scientific knowledge and even just knowledge about the world, that is constantly changing. So like the things that we might have read in our textbooks when we were young or learned when we were in school, they're no longer true. But it turns out underneath all of that change, there are regularities to how what we know grows, how we do science, how errors get rooted out, how things get overturned. And so the idea behind the half-life of facts is that in the same way that when we think about like radioactive materials, like when we have a single atom of uranium, let's say, like I can't predict. I can look at the atom and I can say, oh, I don't know when it's going to decay. It could decay in the next, I don't know, fraction of a second. We might have to wait millions of years. But if I take a whole, like many atoms of uranium or some radioactive material and put them together and get an entire chunk of that material, suddenly it goes from being like entirely unknown to actually quite regular. Like you can actually chart out this half-life of like how long it will take for half of those atoms to decay. It becomes very regular and understandable. And the same kind of analogy and approach can be used when we think about knowledge. And it turns out actually some people have actually tried to study like how long it takes for half of the facts in certain fields to be overturned or become obsolete, or how long it takes for certain scientific papers in different fields to receive half the number of citations they used to. And so there are ways of actually even quantitatively measuring these kinds of things. And so for me, the book, The Half-Life of Facts, was a way to kind of allow people to grapple with and grasp how to think about how knowledge is changing. So rather than saying, oh yeah, I read this fact when I was young, and now people are saying it's not true. And so therefore, I'm just going to kind of throw my hands up in the air and say, we can't understand everything. The truth is, we can understand the world. And in the same way that like science is not a, it's not just, it's not really a body of knowledge. In the end, science is a rigorous means of querying the world around us. And so what that means is that what we know is going to be constantly in a draft form. And so actually, I remember I was talking to a professor of mine from graduate school, and he told me the story where he, I think, went in and gave a lecture on a Tuesday. And then the next day read a paper that actually invalidated everything he had taught the day before. So he went in the next class, like on the Thursday later in the week, and said, "Remember what I taught you? It's wrong. And if that bothers you, you need to get out of science." And so there is this idea like science is constantly in draft form. That being said, there are regularities to how what we know changes. Like it is much more likely that things sort of at the frontier are going to be more subject to being overturned because that's and where we know the least, but it's also where the most exciting things are happening, but it's where the more statistical noise is kind of happening. Things that are kind of in the core of knowledge, they can sometimes be overturned, and that's fine when it comes to science because we're actually sort of asymptotically approaching the truth. But ultimately, there are these regularities. And so the book is kind of trying to promote a means of looking at the world and a way of saying almost like how to learn. Like it's rather than saying here's what to learn, it's how to learn, how to constantly be learning and kind of constantly reevaluating what we know and thinking and maintaining a healthy skepticism. Not we don't want an unhealthy skepticism. Sometimes like too much skepticism is kind of a bad thing too, but trying to kind of grapple with the changing state of knowledge.
I see the connection between the three of your books actually,
Oh yeah.
because the third book is called Overcomplicated. And as I understand it, that is also like kind of like how we should learn or like how we should interact with technology to some extent. Could you sort of explain the core thesis of that book?
Yeah, so that one, and I've actually kind of discussed a little bit of this, of some of the ideas already, which is this idea that, like, and not only are technologies becoming more and more complex, but they are increasingly becoming incomprehensible even to the people who have built these systems or work with them on a daily basis. And so the book looks at sort of what are the forces that lead to this point of incomprehensibility, such as like legacy code and systems being built to be more and more sophisticated or grappling with the complexity of the world around us. And then what do we do? Like, how do we kind of meet these technologies halfway if we cannot fully understand them? And so some of the things around like kind of taking ideas from biology in order to better understand these systems, taking ideas around having a healthy dose of humility towards technology is another kind of feature. And so when I think about technology, oftentimes when people are confronted with a system they don't fully understand, they immediately like zoom off towards two extremes, which one is like fear in the face of the unknown, or this undue reverence and awe. Oh my God, this system I don't fully understand, like this, I don't know, AI technology, it's amazing. And like they almost have this like worshipful attitude towards it. The truth is, you shouldn't have either one. Like, on the one hand, yeah, you can maybe be concerned about these things, but you shouldn't just be like hopelessly worried or fearful. And at the same time, like, you shouldn't be worshiping these systems. Like, they're made by imperfect beings, they're made by us. And like, these things are kind of weird and glitchy or whatever. And for me, not only are these two extremes not great, but they cut off questioning because if you're so worried or so in awe of these systems that you think they're they're kind of like the only thing worth thinking about, you often don't like you're not curious about them. It kind of cuts off a certain amount of questioning and inquiry, while humility says, okay, I might not be able to understand these systems fully, but trying to increase my understanding slowly and steadily, that is still something that can be achieved and is worthwhile. And so, yeah, the kind of the way, whether it's approaching scientific knowledge about the world, knowledge about our own technologies, how we think about software and code, I mean, it all just requires a certain healthy dose of humility as well as curiosity in terms of trying to actually approach these things productively and positively.
Yeah, it definitely connects back to what we talked about before. Since you wrote these books, I mean, it was a few years ago. Have you updated, have you changed your mind on anything since you wrote these books?
Yeah, and so with Overcomplicated, I wrote sort of so that one came out in 2016. So it was certainly well before the heyday of these really complex AI systems. And so I think what I talked about in terms of technological complexity, I feel vindicated there. I kind of feel a little frustrated that I couldn't really like lean into the massive complexity and weirdness of these AI systems, but I think that kind of thing does hold up. I would say, and I would have loved to actually show more examples and kind of really give people a sense of like just the vast complexity of the systems that we're now dealing with. With the Half-Life of Facts, actually, one thing that I wrote in there was I was maybe a little bit pessimistic about certain aspects of science in terms of I actually wrote about how, for the most part, people only, like scientists only receive credit for doing new things rather than trying to do other people's experiments and see if they hold up. Because I was talking about the way in which science, like oftentimes there's a certain amount of noise and sometimes scientific experiments do not necessarily hold up. And since I wrote the book, I don't know, I don't remember the time exactly of the replication crisis or things like that, but there's actually been a much bigger focus on reproducibility in the sciences. And I'm actually really gratified that we're now focusing on that kind of thing. And I'm glad that I was wrong, that like people are now actually being incentivized to actually try to reproduce things like well under like things that they thought were well understood and it turns out maybe they don't actually hold up. And so I think yeah, I would say so like that would be one thing that I would have probably revisited in terms of thinking about that. But yeah.
So I want to sort of bring it all together now. I think I have to read the complete title of your book because basically it's quite a long subtitle. So it's called The Magic of Code, and it's called How Digital Language Created and Connects Our World and Shapes Our Future. And so the point that I wanted to dive into is like the shapes our future part, because this is the existential podcast. So we want to think a bit of what futures do we want to steer towards? Yeah, what do we want the future to look like? So when you think about how code could help shape our future, what do you think are like the most optimistic or like positive cases that you can think of, and how do you think we can like make the most of code, basically?
Well, I love your framing of rather than saying like, oh, like where do I predict things are going, and more about what is the kind of the vision that I want, and then like how can we kind of steer the world towards that or kind of work backwards towards those visions. And so yeah, because I think that's really the key with these kinds of things. It's like we're building them like we so we can be as responsible as possible to actually kind of make the world that we want. And when it comes to kind of code and how we think about these things, I would say, I mean, certain things around AI assisted scientific discovery, I think that actually holds a great deal of potential. We talked about that earlier, but I'm actually very excited about. But I would say another aspect is just around sort of the human-centered aspects of technology. Like right now, because we have such large technology companies, which I mean, in some ways they do some very impressive things, but most people don't really feel like the software is necessarily being like software and code and computing is really being made for them. It's kind of just here's a thing that's imposed from above and like here's the software now go use that. And I think the ability to have like more malleable software or kind of these trends around democratization of software creation, those open the possibilities for creating a much more kind of humane world where people can build the things they want for themselves rather than having to contend with the things that are being given to them that are often sometimes being created for incentives that do not necessarily align with human flourishing. And so for me, I just want I want more software that's kind of in line with our humanity. And so like when I think, and so for example, like when we were talking about like tools for thought or these other kinds of use cases. So there's a TV show a number of years back called *Halt and Catch Fire*, where it was around kind of like the early years of computing. And I think the first year, like it starts in like 1980 and goes through maybe like through the earlier 1990s and so like around like personal computing. And very early on in, I think maybe even like the first episode, one of the characters says, the computer is not the thing. It's the thing that gets you to the thing. And so for me, it's if we focus on the computer itself as like the thing we want to just make more and more powerful, we'll forget that ultimately computers, like, and you look back to like the early days of computing, it was the idea of the computer was in service of making us the best versions of ourselves, helping with ideas around education or tools for thought or simulating and trying to model the world or better understanding of biology or whatever it was. And as long as we keep that in mind and say, okay, this is the reason we have computers. They're for the best hopes of what we're doing, as opposed to kind of just being given these things and not really having that much control. Then I think we're in a good situation. So there's actually, and I think I end the book with, where I talk about this organization called the People's Computer Company. I don't think it was actually even a company, but it was like this organization that ran workshops and published a magazine. But they had sort of their like manifesto or tagline was something about like how computers are for people. And I think we kind of forget that. And so for me, I just, I really want to, alongside all the utilitarian and like enterprise scale software and massive software, let's remember that computers can also be things for people. They can be useful and they can also just be engines and vehicles for delight and wonder. And so as long as we kind of keep those things in mind as we build these systems, then I think things will be kind of, they'll yeah, they'll just be at that right human scale and feel it'll feel a lot healthier.
Yeah, I agree. I think that's a great vision and also probably a great note to end on. Thank you so much, Sam, for coming and talking about this book and all your previous books as well, and for writing the book. We'll share it when we share the episode. And yeah, it was really a recommended read from mine.
Well, thank you so much. This is a lot of fun. And yeah, I appreciate you taking the time to chat with me. This is wonderful.